everyone. So today we are going to discuss about the input impedance, standing wave ratio, and the power calculation for this transmission line. So last class we have discussed more about the lumped parameter for a transmission line, and we have solved few numericals regarding the RLGC parameter and uh, other parameters also we have calculated, like wavelength, phase velocity, and groove velocity, whatever it is. So depending upon this transmission line, few more analysis is left behind with us. That is how to calculate the input impedance of a transmission line at any point. For example, I have drawn a particular diagram. These are the two wire lines, okay, with an input impedance and with the source generator. So generator will provide a particular potential to this particular line, due to which some potential drop will be identified at the load impedance. Here it is indicated as a ZL. This length of the line is Z is equals to L, and our wave is propagating along Z axis. So here I have considered small z is equals to 0, small z is equals to L, and here current is I naught. I naught means at Z is equals to 0 position, what is the potential, what is the current. So at Z is equals to 0 position, V naught is the potential and I naught is the current that we will calculate. Now at the load terminal, Z is equals to L. So what will be my current and load? My load current will be IL and my potential will be VL. Now we have to identify these relations. Okay. Now whenever I will identify this input impedance, I need to calculate the input current with respect to input potential, and with the help of this particular part I can identify the input current. This part means across these two terminal impedance, if I will identify, let us consider that is Zin, or across this point or wherever it is within a particular line, your input impedance is going to look like this. So that means Vg, Zg, and this particular part is indicated as a input impedance, and this input impedance in which the potential drop is V naught. Okay, and what is the current? Current is I naught. So this is the current I naught, this is the potential V naught across the input impedance Zin. So with the help of this figure, we can easily calculate the input impedance for a two-wire transmission line. Similarly, the standing wave ratio can also be calculated. Now why it is called standing wave ratio? Standing wave ratio means it is the ratio between the maximum potential with respect to the minimum potential. A point within this particular line will be identified at a certain point in which your maximum potential means incident potential with respect to the reflected potential, if it is remain constant, then we will say it is called as a standing wave. And the ratio itself indicates that either we can go for voltage standing wave ratio or current standing wave ratio. VSWR and CSWR. VSWR is a ratio of a maximum potential with respect to the minimum potential, Vmax by Vmin, not incident, not reflected. It is a maximum potential with respect to the minimum potential. Okay. Similarly, current standing wave ratio itself indicates that it is a ratio of a maximum current with respect to the minimum current, and that particular point will be identified within this transmission line. That also we can calculate. And one more important thing, our main target is what? Maximum how much power we can deliver to the load. So power calculation is also there. Now how we will proceed all these things? We will proceed all these things with the help of the wave equation what we have derived in the previous classes. So wave equation what we have written, let me write once again. One is d square Vs of z by dz square is equals to gamma square Vs of z. Okay, and the current wave equation is d square Is of z divided by dz square is equals to gamma square Is of z. So these are the two basic wave equations through which we can proceed to calculate the input impedance, standing wave ratio, and the power calculation. Let's see. Now first of all, these two equations you need to solve it. The solution need to be identified so that the position wise we can identify what is the potential, what is the current. So here the solution of equation 1, Vs of z is equals to V naught plus e to the power minus gamma z and V naught minus e to the power plus gamma z. So this is the solution of first equation. Similarly, the solution of second equation, Is of z is equals to, directly I am writing V naught plus divided by z naught e to the power minus gamma z and minus V naught divided by z naught e to the power plus gamma z. So these equations already we have discussed in the previous classes. So directly I am writing the values. Okay. Now once these two equations are known, with respect to the position we can identify what is our V naught and what is our I naught. Okay. How? Let's see. Let us consider the point at z is equals to 0. So what I will write? At z is equals to 0, that means Vs of 0 is equals to how much? In place of z we have substituted Vs of 0. E to the power 0 means it is 1. So here I will get V naught plus and here it is V naught minus. This is with respect to first equation, means this equation. Similarly, Is of 0 is equals to V naught divided by Z naught minus V naught divided by Z naught. So these are the two equations. So with the help of these two equations, you can easily identify what is the V naught plus and what is V naught minus. Once this V naught plus and V naught minus is known, you can easily identify what is I naught plus and I naught minus. Okay. Okay. So our first equation at z is equals to 0. Okay. This is the equation and this is one current equation. Okay. So Vs of z at 0, that means at z is equals to 0, what is the potential? V naught. So I have written V naught. Okay. Similarly, at z is equals to 0, what is our current? That is I naught. Okay. Here I have written I naught. So with the help of these two equations, we can easily determine what is V naught plus and V naught minus. Let's see how to calculate it. It is simple quadratic equation, so we can easily solve it. Let me erase these two equations. I don't require these two equations. From these two values, so here it is V naught is equals to V naught plus and V naught minus. I naught is equals to V naught plus divided by Z naught minus V naught divided by Z naught. First you add these two, then subtract these two. So easily we can determine V naught and V naught plus and V naught minus. So after solving above two equation, we will get V naught plus is equals to half of V naught into I naught minus V naught minus Z naught into I naught. So this is the first case. Similarly, V naught minus is equals to half of, this is plus, V naught minus Z naught into I naught. So these are the 7th and this is 8th equation. So these are the two equations through which the incident potential and the reflected potential can be identified. At which particular point? At z is equals to 0 point. So this is the incident potential. Here I will write incident in some of the book this incident is also called as forward, and this is called as a reflected one, which is called as backward. Okay, so with the help of these two V naught plus and V naught minus, we can easily calculate our input impedance. Okay. Okay. So here the input impedance can be calculated at any point of the transmission line. At this point, at this point, at this point, and any point. Okay. Let us consider at z is equals to 0, we are calculating the input impedance. Okay. So at z is equals to 0 means my loop will be end up in this particular circuit. That means I have written this particular diagram from this. So here I have the generator, here I have Zg generator impedance and I0, and this particular impedance is indicated as a Zin, in which the potential drop is V0. Okay. Now with the help of the circuit you can easily identify what is I0 and what is V0. I0 is what? The total current which is within this circuit. Okay. So what is I0? I0 is nothing but Vg divided by the total impedance. Total impedance is how much? Zg plus Zin. So here I have written I0 is equals to Vg divided by Zin plus Zg. Okay. Similarly, you can easily identify what is the potential drop across this Zin, that is V0. So V0 is equals to how much? I0 into Zin. So what is our I0? Vg divided by Zin plus Zin. Substitute here. So here you will get V0 is equals to Zin whole into Vg divided by Zin plus Zg. So these are the two basic equations at any point of a transmission line can be identified. So here at z is equals to 0 I have identified. Now we can move for z is equals to L. L can be any point between z is equals to 0 to L. So here you can identify L1, L2, L3, L4, different number of positions. With a different number of positions your impedance is going to change. But one thing which is remain constant, that is your propagation constant will remain constant throughout the system, and your characteristics impedance of this line will remain constant throughout the system, because your RLGC parameter is not going to change, it remains constant. So your characteristics impedance and propagation constant means gamma and Z0 will not change with respect to the position. It is independent of the position. Okay. Now with the help of these two, we will proceed to determine if at Z is equals to L, what is our potential and what is our current. Okay. 1 minute. So now we are going to calculate the input impedance at Z is equals to L. Z is equals to L means at the load point. Now let's see how to identify this. As we have the relation Vs of Z is equals to V0 plus e to the power minus gamma Z plus V0 minus e to the power plus gamma Z. This is the first solution. Similarly, Is of Z is equals to V0 plus divided by Z0 e to the power minus gamma Z minus V0 minus divided by Z0 e to the power plus gamma Z. So these are the two solutions. Now what we have to do, as we have done for Z is equals to 0, substituting the value of Z as 0, and we have calculated our V0 plus and V0 minus. Similarly, here also we are going to calculate it. So at Z is equals to L, Vs of L, V0 plus e to the power minus gamma L plus V0 minus e to the power plus gamma L. Similarly, Is of L is equals to V0 plus divided by Z0 e to the power minus gamma L minus V0 minus divided by Z0 e to the power plus gamma L. Done. Now with the help of these two equations, let the equation is 9 and 10. This is, let us consider 11 and 12. Okay. So with the help of these two equations, you can easily determine what is V naught plus and V naught minus. So let me write the V naught plus, rearranging above equation, it is half of Vs of L plus, or okay, Z naught Is of L whole into e to the power gamma L, and V naught minus is equals to half of Vs of L minus Z naught Is of L, e to the power minus gamma L. So these are the two equations. Now we will write all these equations in terms of VL and ZL, because at load point the potential drop, that is Vs of L, is nothing but VL. Okay, let me write. So Vs of L, I can say it is potential drop at the load point. Then Is of L, I can write it is current across the load terminal. So what I will do, I will write V naught plus is equals to half of VL plus Z naught into IL e to the power gamma L, and V naught minus is half VL minus Z naught IL e to the power minus gamma L. So this is my 13 equation, and this is equation number 14. So these are the two equations we have identified at load terminal: incident potential and reflected potential. Okay. Now here the most important factor is the reflection coefficient will come into picture. Reflection coefficient always measured at the load terminal. Okay. Now what is the reflection coefficient? Reflection coefficient is a ratio of reflected potential with respect to the incident potential. So if I will take a ratio of V naught minus divided by V naught plus, then I will determine the reflection coefficient easily. Okay. So that we will calculate. First we will discuss how to identify these particular points. Okay. So once this V naught and V naught plus is identified, then you can proceed to determine the input impedance at the load point. At that point also you can identify the input impedance, because input impedance will change with respect to the position of length, as we have seen in that figure. So here if I will write Vs of Z divided by Is of Z is equals to Z in. So this relation itself indicates that at any position of Z you can identify the input impedance. Okay. So this Z in, if I will write input impedance at Z is equals to 0, here I will write Vs of 0 divided by Is of 0, which is equals to V naught by I naught. Simple. Similarly, if I will write input impedance at Z is equals to L, then Vs of L divided by Is of L, which is nothing but load potential divided by the load current. So input impedance can also be calculated at any point of the Z. From Z is equals to 0 to Z is equals to L. At any point or any position of that particular line, you can easily calculate the input impedance. But this relation is not sufficient to justify the input impedance is varied with respect to the position. Now we have to derive this relation. Okay, we have to identify this relation. We have to substitute all these parameters here. What will be in terms of V naught plus and V naught minus, because anyway at the end we have to represent in terms of reflected potential and incident potential. Okay. Okay. So here at Z is equals to L, how to identify the input impedance? So Vs of Z divided by As of Z. as we know that V naught by I naught is this much. Okay. Now at change with respect to the position, your V naught plus and V naught minus is also going to change. As we have written, V naught plus for the load terminal where Z is equals to L, half VL plus Z naught and IL and e to the power gamma L. Similarly, V naught minus is half VL minus Z naught IL into e to the power minus gamma L. You need to substitute this value in this equation. That's it. So in place of V naught plus, substitute this value. In place of V naught minus, substitute this value for numerator as well as for denominator. Rearrange this whole factor. Rearrange means if I will take this IL common from the upper part. So VL by IL I will get VL by IL is nothing but ZL. So wherever that VL by IL will come, replace it by ZL. So here I will get ZL plus Z naught. Similarly, here ZL minus Z naught. And e to the power minus gamma L, e to the power minus gamma L over. Similarly, in denominator also, take that IL common and that IL and this IL will be cancelled out. Here also VL by IL means again it will become as a ZL and here it will become as a ZL minus Z naught. So that means my equations will become this form. So first Z naught, numerator I am writing half of ZL minus Z naught e to the power gamma L, then plus half of ZL minus Z naught, this is plus e to the power minus gamma L, okay, whole divided by half of, here also VL by IL is ZL plus Z naught e to the power gamma L minus half of ZL minus Z naught e to the power minus gamma L. So this is the input impedance we are calculating where Z is equals to L. Okay. Now here what happens? Here e to the power gamma L and e to the power minus gamma L is there. Rearrange it. Take the common of ZL common and Z naught common from numerator also as well as for denominator. So if I will take ZL common, so it is half e to the power gamma L and here it is half e to the power minus gamma L, one component will come. And if you take that Z naught common, half e to the power plus gamma L and minus half e to the power minus gamma L, one more component will come. Okay, let's see how these components will identify these relations. So first of all, for the input impedance, numerator I am taking ZL common. So if it is ZL common, half of e to the power gamma L, then from this plus e to the power minus gamma L. So this is first one, plus Z naught. Z naught is there, so take half e to the power gamma L minus e to the power minus gamma L. So this is the numerator part. Similarly, for denominator, ZL is equals to ZL of e to the power gamma L plus e to the power minus gamma L, like this. And here, due to the presence of minus, so half ZL and minus ZL. So this is minus, it will come here, and then plus Z naught half e to the power gamma L, and this half will be plus e to the power minus gamma L. So this is the relations we are getting. Now what is this? Half of e to the power gamma L plus e to the power minus gamma L is one component. E to the power gamma L minus e to the power minus gamma L is one component. So here I can write e to the power plus gamma L plus e to the power minus gamma L divided by 2 is called as cos hyperbolic gamma L. Similarly, e to the power plus gamma L minus e to the power minus gamma L divided by 2 is sin hyperbolic gamma L. So this is as we are taking e to the power j theta plus e to the power minus j theta divided by 2, which is cos theta, but since it is a complex value, so we are taking in a cos hyperbolic formula. So it is cos hyperbolic gamma L, this is sin hyperbolic gamma L. Only now we have to substitute here. Okay. So let us substitute the values. So my input impedance is equals to Z naught. First is ZL. This is plus, it is cos hyperbolic gamma L plus Z naught sin hyperbolic gamma L. Done. Divided by ZL, this is sin hyperbolic gamma L, and this is Z naught cos hyperbolic gamma L. Done. Now if you divide these two, we will get 10 hyperbolic gamma L, which is equals to e to the power gamma L minus e to the power minus gamma L, e to the power gamma L plus e to the power minus gamma L. So what I will do, I will take this cos from the numerator as a common and denominator as a common. So what I will get? Z naught, this is ZL, Z naught 10 hyperbolic gamma L whole divided by, this is ZL 10 hyperbolic gamma L plus Z naught. Okay. Now I will rearrange it. So Z in is equals to Z naught ZL plus Z naught 10 hyperbolic gamma L divided by Z naught plus ZL 10 hyperbolic gamma L. So this is my input impedance for the transmission line in which at any point within from Z is equals to 0 to L. If you change the value of L, your input impedance is going to change. But your load impedance and your characteristics impedance remain constant throughout the system. So this is the general equation for the input impedance. Now as I have discussed previously, there are three different type of lines are there. One is lossy line, one is lossless line, one is distortionless line. Here whatever we are discussing, it is discussed about the lossy line. It is a general case. Okay, so it is a general input impedance, general case, or you can say it is called lossy line, because in lossy gamma value will be there, but in lossless your gamma value depend upon only the function of imaginary component. Real part attenuation constant is going to be 0. So this is the input impedance what we have identified. Done. Next we will calculate the standing wave ratio. Okay. So whatever the input impedance we have calculated, it is a general case or it is for lossy line. Now we will see the change in parameters. Okay, so this is for lossy line. Once again I am writing for lossy line input impedance Zin is equals to Z naught ZL plus Z naught 10 hyperbolic gamma L Z naught plus ZL 10 hyperbolic gamma L. Done. So this is the general case for lossy line. Similarly, we can also write for lossless line. Okay. So what is the condition for the lossless line? So for lossless line, so first we need to identify the condition. So for lossless line, your R is equals to G is equals to 0, due to which your propagation constant gamma, which is R plus J omega L, G plus J omega C, if you substitute this condition, we will get root over of j omega root over of LC, which is equals to alpha plus j beta, and alpha is 0 and beta is equals to omega root over of LC. Done. Now, what will be our input impedance for this sort of lossless line? So here we have a parameter called 10 hyperbolic gamma L. So here I will substitute 10 hyperbolic in place of gamma. I will write j beta into L. Done. This 10 hyperbolic of imaginary component I can write j10 beta L. So that means the 10 hyperbolic gamma L is equivalent to j10 beta L, and it is only possible if the line is lossless line. Okay. So here I will substitute input impedance Z0 ZL plus j Z0 10 beta L divided by Z0 plus j ZL 10 beta L. Done. So this is the input impedance for lossless line. Lossless line. Done. So we have to identify the condition first. Then we have to substitute the propagation constant value. Then what will be our 10 hyperbolic gamma L? Substitute the value, you will get j10 beta L, and I can write the input impedance in this sort of form. Okay. Now here one more important factor, beta L. In question they will ask what is electrical displacement. Electrical displacement. So electrical displacement is nothing but beta L. What is beta? Beta is radian per meter. What is L? L is in meter. So what is the unit of this electrical displacement? Electrical displacement will be in radian. Okay, because it is a product of, it is a electrical displacement or electrical length. Sometimes they will ask calculate the electrical displacement, so you need to calculate beta L. Sometimes they will call it as electrical length, so electrical length means beta into L. Both are same. Or I will write electrical length. Okay, so this is the part for lossless line, and this is the calculation for lossy line. Now once this input impedance is known, next we will go to reflection coefficient, and then we'll go to standing wave ratio, and then we can easily find out the power. Okay. Okay. So reflection coefficient at load, as I have told that it is a ratio of a reflected potential with respect to the incident potential. So reflected potential, if I will see with respect to this wave equation solution, from that I can identify which one is the incident and which one is the reflected. So here you can see V0 plus e to the power minus gamma L, it indicates that it is an incident one. Similarly, V0 minus e to the power minus gamma L is called as reflected one. So if you take the ratio of a reflected with respect to incident, and it is called as a reflection coefficient. And reflection coefficient is always calculated at load end. Okay, at load end, not at receiver end. At load end means receiver end. So not at generator end, I mean to say. So this reflected by incident we will get as a reflection coefficient. Now what is V0 plus and V0 minus with respect to VL and IL, what we have written? Okay. Now V0 plus is equals to half of VL Z0 into IL e to the power gamma L, and V0 minus half of VL minus Z0 into IL e to the power minus gamma L. So these are the two relations. Done. So now what you have to do? You have to substitute this value here. If you are going to substitute this value, e to the power V0 plus is here, substitute here. So I will get reflection coefficient V naught minus is half VL minus Z naught into IL e to the power minus gamma L, and here it is plus e to the power gamma L. It will be cancelled out. Done. Divided by what is V naught plus? V naught plus is half VL plus Z naught into IL e to the power gamma L, but here it is e to the power minus gamma L. So it will be cancelled out. So this half will be cancelled out. Now take this IL common from numerator and denominator. So you will get VL by IL is nothing but load impedance, ZL. So if you rearrange this, you will get ZL minus Z0 divided by ZL plus Z0. So this is called my reflection coefficient at load. Done. Reflection coefficient at load. It depends upon load impedance and it depends upon the characteristics impedance. So its basic relation is what? ZL minus Z0 divided by ZL plus Z0. This is at load terminals. Now similarly, reflection coefficient you can measure at input side also. But the difference will be what? In the difference, this ZL will be replaced by Zin and Z0 will remain as it is. Okay, so that is the reflection coefficient at input impedance. This is the reflection coefficient at the load impedance. Okay, so this is the basic calculation for the reflection coefficient. Now we will see what is our standing wave ratio. So next is standing wave ratio. Okay, so standing wave ratio, either we can go for voltage standing wave ratio, that is called as a VSWR, which indicates that it is a ratio of maximum potential with respect to minimum potential. Okay, so it is 1 plus reflection coefficient at load divided by magnitude of reflection coefficient at load. This is the basic relation. Okay, so this is the basic relation of your VSWR. Similarly, current standing wave ratio also you can write CSWR. V is directly proportional to I, so you can write it is I max by I mean, which is equals to same as 1 plus reflection coefficient divided by 1 minus mod of reflection coefficient. So this is the standing wave ratio. Next, reflection coefficient at input end, as I have told, reflection coefficient at input at Zin. If I will calculate reflection coefficient at Zin, so what will be the difference? At input end, ZL is only replaced by Zin. Zin minus Z0, Zin plus Z0. So this is my simple relation with respect to the reflection coefficient at input end. Okay, so these are the small relations through which we can identify our various other relations depend upon the nature of lines. So this is my reflection coefficient at load, reflection coefficient at input end, and the standing wave ratio. So next is the power calculation. It is a simple one. So average power you can calculate with the help of Poynting theorem also. In Poynting theorem E cross H we are writing, but here we are writing in terms of V into I. So it is half of real value of Vs of Z into complex conjugate of Is of Z. Now Vs of Z and Is of Z we have known. Just we need to multiply it and we have to get the result. So directly I have written V0 square divided by 2Z0 whole into 1 minus reflection coefficient square. And if you separate these two terms, one is V0 square divided by 2Z0, that is called incident power, and V naught square divided by 2 Z naught into reflection coefficient square, that is called reflected power. So incident power minus reflected power is equals to the transmission power. So here I can write power transmission. So transmission power is equals to incident power minus reflected power, that I can write. So PT is the transmitted power, PI is the incident power, and PR is the reflected power. So what is the incident power? It is V naught square divided by 2Z naught. And what is the reflected power? It is V naught square divided by 2Z naught whole into reflection coefficient square. So this is the relation between the transmission power with incident power and reflected power. Now when we are calculating what is the total power delivered, so delivered means indirectly is asking about transmission power. So what is the transmission power? Transmission power is a difference between incident power and the reflected power. So this is the power calculation. Okay. Now we have calculated input impedance for lossy line, input impedance for lossless line. Then we have calculated what is the reflection coefficient at the load, the reflection coefficient at the input side, standing wave ratio, and the power calculation. But apart from this, there are few special cases through which we have to identify the relations. Okay. Now here I will write classifications of lines. Okay. Types of lines we have seen: lossy line, lossless line, distortionless line. Okay. But classifications line depend upon the characteristics of that line. Means it depend upon the nature of load. It will identify. First is open circuit line. Okay. Second is short circuit line. And third one, most important factor, that is called matched line. Okay. So these are the three classification of lines depend upon the characteristics of load. If the load is not there, that means it is called as open circuit. If load is short circuit, that means the potential is zero, then we can say it comes under our short circuit line. And match line means some conditions are there, that we will see. So first we will discuss about the transmission line. So let me draw first. So this is my transmission line. Okay, two-wire transmission line. Two-wire transmission line. Then in this two-wire transmission line, your gamma and characteristics impedance remain constant. Then now this is my input side. I will write Zin. Then now here this is my load impedance. Okay. So here I will write IL. Here I will write VL plus minus. This is potential. This is ZL. Done. Now, depend upon the characteristics of this load, we are going to identify what is open circuit line, what is short circuit line, and what is match line. So first I am discussing about open circuit line. Open circuit line means your load impedance is infinite, means there is no load impedance. This is first line, this is second line, two-wire line, and there is no load. Okay, there is no load. Load is open, means there is no load. So here ZL is equals to infinite. So here it is gamma, here it is Z0. So if ZL is infinite, first I am going to identify what is the input impedance for this. And for all these cases I am considering the line is lossless line. Lossless line. Done. So lossless line condition is what? That we have already identified. So first I will write Z0, which is multiplied with ZL, J Z0 10 beta L. Directly I am writing for the lossless line. So this is the input impedance for the lossless line, but depend upon the nature of the load, the lines are identified. Okay. So here I will write Z0 plus J ZL 10 beta L. Done. For lossless, what are the conditions that I will write first? Gamma is equals to J beta. Beta is equals to omega root over of LC. So that I have substituted 10 hyperbolic gamma L will become as a J 10 beta L. Now, as per the consideration, load impedance is infinite. So here ZL is infinite. So what we will do? We will take this ZL outside. Okay. If I am taking outside from numerator and denominator, it will be cancelled out. So Z0 1 plus J Z0 by ZL 10 beta L. This is the numerator part. Then Z0 divided by ZL plus J 10 beta L. This is the denominator. Done. Now ZL is infinite. Something by infinite is 0. So that means this part is tends to 0 and this part is tends to 0. So what we have left? We have left with Z0 divided by J10 beta L. Done. Now take this J10 beta L to above. So if you take above, in numerator it will become minus J Z0 cot beta L. So this is the input impedance for the open circuit line, which is lossless in nature. So here I can write it is called ZOC. So ZOC is minus J Z0 10 beta L. Okay. So this is my open circuit input impedance, which I have written as a ZOC. Done. So first is input impedance we have calculated. Second, reflection coefficient we need to calculate. So what is our formula? It is ZL minus Z0 divided by ZL plus Z0. Done. Now what is same principle? Take ZL common from numerator and denominator. So Z0 by ZL will come. Something by infinite is 0. So my reflection coefficient is 1 minus 0, 1 plus 0. So my reflection coefficient for the open circuit line is 1. Okay. Similarly, I need to calculate the VSWR for the open circuit line. So third is VSWR. So its relation is 1 plus reflection coefficient at load minus reflection coefficient at load. Done. So here reflection coefficient is 1. So 1 plus 1, 1 minus 1. So something by 0 is infinite. So my VSWR is infinite. Reflection coefficient is 1. VSWR is infinite. And what is my input impedance? ZOC is equals to this much. Now similarly, we can calculate for short circuit line. Short circuit line. Now what it indicates? Short circuit line means your load impedance is 0. Okay. How it will look? Let's see. So this is my line, transmission line. This is my transmission line, two-wire line. I am considering gamma and Z0. And there is no load, but it is short circuited. So this is short circuited. Okay. So if it is short circuited, the load impedance is 0. Now again, since it is a lossless in nature, So what will be my input impedance first? So input impedance, general equation, let me write ZL plus Z0 10 beta L divided by Z0 plus ZL 10 beta L. Done. Now since ZL is 0, substitute the ZL value. So if I am substituting, this value is 0 and this value is 0. So we have left with Z0 and this value. So Z0 will be cancelled out. It will become J Z0 10 beta L. So this I can write ZSC. ZSC means input impedance for short circuited line. So this is my input impedance. Similarly, reflection coefficient I can write ZL minus Z0, ZL plus Z0. So ZL is 0 means minus 1 I will get. And what is my VSWR? Again the same relation, 1 plus reflection coefficient at load, 1 minus reflection coefficient at load. So it is minus 1 means mod. So 1 minus 1, again it is infinite. So VSWR, again it become infinite. Okay. Reflection coefficient is minus 1. So what is the difference between open circuit and short circuit? Open circuit and short circuit, VSWR is infinite. Reflection coefficient, for this it is plus, for this it is minus 1. Input impedance is minus J Z0 cot beta, sorry, it is cot. It is cot beta L, and here it is J Z0 10 beta L. Okay, so these are the two different sort of lines, and one more line which is called match line, that we will see how, what are the parameters are there. So match line means there will be a load ZL whose value is equals to Z0, and this is the case when maximum power is delivered. When the maximum power is delivered, when the transmission line characteristics impedance is equals to the load impedance, then only the maximum power is delivered. So for this case, it is matched line, that is ZL is equals to Z0. So this is my last line. Done. So what I will do, it is a lossless line. So ZL is equals to Z0. If you substitute here ZL, everything it will common. So here I will get Zin is equals to Z0. This whole term will become 1. So Zin is equals to Z0. Okay. So this is for match line. Then what will be my reflection coefficient? That is ZL minus Z0, ZL plus Z0. So this is become 0 because ZL is equals to 0. There is no reflection. And this is the case in which maximum information can be delivered without any reflection. It indicates that if reflection coefficient exists, means losses will be there. Reflection value will be there, which will act as a noise component, which will hamper our information while we are delivering the total quantity of information at a load terminal. But when the characteristics impedance of a line and a load is equal, then we can say reflection coefficient is 0 and maximum power is delivered without any sort of reflection. But practically it is not possible. It is theoretical calculation. Practically reflection losses will be there, but we have to minimize that reflection coefficient with some sort of arrangements. Okay. Then VSWR is equals to 1 plus reflection coefficient 1 minus reflection coefficient. For match line VSWR is 1, for other line VSWR is infinite because reflection coefficient is there. Similarly, in this reflection coefficient is 0, maximum power can be delivered from input end to the load end because we are matching the characteristics impedance of the line and the load terminals. Okay, so these are the basic relations through which we can justify our answers. And as we have written, ZOC is minus J Z naught cot beta L, and ZSC is J Z naught tan beta L. If you multiply these two, ZOC and ZSC, cot beta L and tan beta L will be cancelled out with each other. Minus J and plus J will be cancelled out, and we will have only, because this J into J will become minus 1 and minus minus plus, and we will have Z naught square. So characteristics impedance I can write directly as ZOC into ZSC. So this is one more relation between characteristics impedance with short circuited impedance and open circuited impedance. This relation will help us to solve various number of numericals, what we are going to discuss in the next class. But for the time being, these are the certain relations. Okay. Okay. So these are the certain relations what we have discussed today with respect to input impedance, with respect to reflection coefficient, standing wave ratio and other parameters. Next class we are going to discuss few numericals and the type of transmission lines. Means here we have identified the classifications. We have half wave transformer and quarter wave transformer. So that transformer is nothing but a transmission lines, where it is a part of a transmission line, and that part, it depends upon the length. If your length is lambda by 2, then I will say it is called half wave transformer. If the length is equals to lambda by 4, then it is called quarter wave transformer. And in place of this L, you have to substitute that value. So if you are substituting lambda by 2, that means for half wave transformer we are calculating the parameter. Similarly, if the length is calculated for lambda by 4, then we are calculating for a quarter wave transformer. For the time being, we'll end up at this. Tomorrow we will continue with respect to the numericals, with respect to these all derivations what we have done. Okay, thank you all.